case of the first one is T1, and the temperature of the second one is T2. Now, the total emissive powers were EB1 and EB2 respectively. Rate at which the radiation is emitted by a body and absorbed by body 2. Now, if it is a black body, it is going to absorb all the radiation, you know that. So when the radiation is going from body 1 to 2, the rate at which the radiation is emitted by body 1 and absorbed by body 2, which we are calling as Q12 because it is going from 1 towards 2, is equal to A1, EB1 and F12. Now, EB1, later we will see that this EB1 will be equal to sigma T1 to the power 4. And till then, see, we have not written an emissivity out here. That is because that for a black body, emissivity is equal to 1. So Q12 is equal to A1, EB1 into F12. And the radiation rate at which the radiation is emitted by body 2 and absorbed by body 1 is written as Q21, and this is A2, EB2, F21. So the net rate of heat exchange is A1, EB1, F12 minus A2, EB2, F21 in that particular direction. Now we have seen that EB1 is equal to sigma T1 to the power 4 and EB2 is equal to sigma T2 to the power 4. And from the reciprocity rule of view factors, we know that A1 F12 is equal to A2 F21. So A1 F12 is equal to A2 F21. So they can be taken as common. So I take this as common and write it as A1 F12. And in the brackets, I can write it as EB1 minus EB2. Now I put in the values of EB1 and EB2 as sigma T1 to the power 4 minus sigma T2 to the power 4. So now what we have is that Q, that means the rate of heat transfer or radiation heat transfer between two bodies which are at temperatures T1 and T2 is equal to A1 F12 sigma T1 to the power 4 minus T2 to the power 4 in case that both the bodies are black bodies. Now, if the bodies are infinite parallel plates, that means if there's a one plate like this, the second plate is like this, but they're all infinite. So they're extending in this direction, and this is extending in this direction, and this is also extending in this direction, and this is also extending in the other direction. Okay. So these are infinite plates. So whatever comes out of 1 is going to fall on 2, and whatever comes out of 2 is going to fall on 1. So in this case, F12 is equal to F21 is equal to 1. So if I put in this value of F12 equal to 1, the expression gets a little more simplified, and the rate of heat transfer is equal to A1 into sigma T1 to the power 4 minus T2 to the power 4. So if there are two black bodies exchanging heat amongst each other, and you're asked to calculate the rate of heat transfer, then that Q is going to be A1, that means the area of the first body, into F12 sigma T1 to the power 4 minus T2 to the power 4. We're considering the T1 has got a greater temperature than T2. And if it's the other way around, we can also do that same calculation. And because we know that A1 F12 is the same as A2 F21. So this is more or less simple when the two bodies are black bodies. Now let us see if the bodies are non-black bodies. But what kind of bodies are they? They are gray bodies essentially. If you remember, I had told you that gray bodies are also ideal situations, but the emissivities in this case is not equal to 1, it is less than 1. It figure tha jisme we had seen that emissivity was equal to 0.6. It could be 0.6, it could be 0.5, 0.7, whatever, but less than 1. And these are, we are trying to understand the radiation heat exchange between two parallel gray planes. That means one plane is here and one plane is here. There are two planes. They are parallel to each other, which means the distance between them remains constant. And these two planes are non-black. They are essentially gray bodies. And so if they're gray bodies, their emissivities are going to be different. So if for body, the lower one is called plate 1 and the upper one is called plate 2. So the emissivity of the lower one is going to be epsilon 1 and the upper one is going to be epsilon 2. And what will happen that when if it was a black body, then whatever radiation was falling on it, all of it would be absorbed. But since this is not a black body, it is a gray body, part of it will be absorbed, part of it will be reflected, and part of it could also be transmitted. But in this case, we are not talking about transmission. We are only talking about we are thinking that there will be no transmission in this case. There is only absorption, and part of it will be reflected. Reflected or radiated back to the source. Now, if the emissivities or absorptivities of plane 1 and 2 are epsilon 1 and epsilon 2, and alpha 1 and alpha 2, alpha 1 and alpha 2 are the absorptivities, and epsilon 1 and epsilon 2 are the emissivities. So from Kirchhoff's law, we can say that epsilon 1 is equal to alpha 1 and epsilon 2 is equal to alpha 2. The areas of the two bodies are A1 and A2, and the view factors are F12 and F21, and both of which are equal to 1 because these are parallel bodies. Whatever radiation comes out from 1 will essentially fall on 2. There is no other place to go. And whatever comes out from 2 will fall on 1 because, again, there is nothing else to go. So let us see what happens out here. So I have tried to put colors to these different lines, and the values associated with each of these colors, I've also tried to color code it. So you will find it slightly easier to understand what I'm talking about. Now let us start from body 1. Body 1, which has got a temperature of T1 out here, and body 2, which has got a temperature of T2 out here. So the radiation energy that is emitted from 1. So this is the first, let's look at the first blue arrow. Let me get my pointer laser. So the first thing is, this is the amount of radiation that is coming out from body 1 and going towards body 2. This is equal to epsilon 1 A1 sigma T1 to the power 4. And why is it there is an epsilon 1? Because this is a non-black body. So a non-black body, but why don't we include the view factor? Because the view factor in this case is essentially equal to 1. Otherwise, there would have been a view factor out here also. So without the view factor being equal to 1, the radiation that is coming out of body 1 and falling on the second plate is given as epsilon 1 A1 sigma T1 to the power 4. This whole unit together, I'm terming it as X because it's easier for me. Itna likh nahi sakte, there's not enough space. Now, once this radiation falls on plate 2, part of it will be absorbed, which is shown by the green arrow, and part of it is reflected back, which is shown by the red arrow. So how much will be absorbed? Whatever is falling multiplied by the absorptivity. So energy absorbed by A2 out here, if you notice, where I'm right now got my pointer, is equal to, this is the whole amount of energy that is coming multiplied by the absorptivity, which is alpha 2. Now, according to Kirchhoff's law, we have seen that alpha 2 is the same as epsilon 2. That means the absorptivity is the same as the emissivity. So we can write, instead of alpha 2, I'm writing it as emissivity, that is epsilon 2. So this is epsilon 2 into epsilon 1 A1 sigma T1 to the power 4. Or in green, I have written it as epsilon 2 into the whole term, which is in terms of X. And I had already told you what is X. X is epsilon 1 A1 sigma T1 to the power 4. Now, if epsilon 2 amount is absorbed, how much is reflected? The rest of it is reflected because I said we have considered transmittance to be equal to 0. So the rest of it will be, I told you, if you remember, that if radiation falls on a body, there are 3 possibilities. One is that it can be reflected. One is that if it is non-opaque, then it can get transmitted. And one is that it is absorbed. So if transmittance is equal to 0, then there are 2 possibilities. One, it will be that it can be absorbed. And the second part is that it can be reflected. So if part of it is absorbed, which is epsilon 2, the rest of it is reflected back. So rest means 1 minus epsilon 2 part is reflected back. And so energy reflected back by A2 to A1 is equal to 1 minus epsilon 2 into X. So once this falls on the, again, which plate is this? This is now getting reflected from plate 2 and it's falling on plate 1. So what happens after that? Let's see. So once it falls on plate 1, again, part of that energy will be absorbed and part will be reflected back. So how much is absorbed? Energy absorbed by A1 is equal to this amount of energy that is coming out here multiplied by the absorptivity of plate 1 which is again equal to the emissivity according to Kirchhoff's law. So this becomes epsilon 1, 1 minus epsilon 2 into x, x being epsilon 1 A1 sigma T1 to the power 4. Again, whatever is falling, part of it is absorbed, like I said, and part of it is reflected. So if epsilon 1 amount is absorbed, 1 minus epsilon 1 part is reflected. So the part that is reflected is now 1 minus epsilon 1. So this is 1 minus epsilon 1 into 1 minus epsilon 2 into x, which is essentially epsilon 1 A1 sigma T1 to the power 4. So this is where have I come? I have come till this part. This is the part that is reflected from plate 1 and it goes back to plate 2. Again, part of it will be absorbed, part of it will be reflected. How much is absorbed? The amount that is absorbed, whatever is falling, uska epsilon 2 part is going to be absorbed. Actually, essentially, it is an alpha 2 part which is absorbed, but alpha 2 becomes equal to epsilon 2, so epsilon 2 part is absorbed, and 1 minus epsilon 2 part is reflected back. So the part which is absorbed is epsilon 2 into 1 minus epsilon 1 into 1 minus epsilon 2 into x. That means this amount into epsilon 2. And the part that is reflected back from plate 2 to plate 1 again is 1 minus epsilon 2 into 1 minus epsilon 1 into 1 minus epsilon 2 into x. Again, whatever falls out here, epsilon 1 part is absorbed. Actually, alpha 1 part is absorbed, alpha 1 being equal to epsilon 1, and the 1 minus epsilon 1 part is reflected back. So what is the part that is absorbed? Epsilon 1 into 1 minus epsilon 2 into 1 minus epsilon 1 into 1 minus epsilon 2 into x. And what is reflected? 1 minus epsilon 1, 1 minus epsilon 2, 1 minus epsilon 1, 1 minus epsilon 2 into x. Or we can say 1 minus epsilon 1 square into 1 minus epsilon 2 square into x. Again, epsilon 2 part of this amount is absorbed, the rest is reflected. And this, since these are parallel plates, this is going to continue for infinity. So now let us look at if this continues and the total energy sent. Now we are trying to understand what is the total energy sent from 1 and is absorbed by 2. So what is the total amount of energy which goes from 1 and is absorbed from 2? So we are just looking at the green arrows out here. These 3 green arrows which are falling on plate 2. So this is Q12. Look at the first green one. What is it? This is epsilon 2 into x. What is the second green one? Epsilon 2 into 1 minus epsilon 1 into 1 minus epsilon 2 into x. What is the third one? Epsilon 2 into 1 minus epsilon 1 into 1 minus epsilon 2 into 1 minus epsilon 1 into 1 minus epsilon 2 into x plus, and this goes on forever. Now I have put in the value of x in this top equation, and just written instead of x, I've written epsilon 1 A1 sigma T1 to the power 4. So if you look at the first term, what does it come out to be? It is epsilon 1 epsilon 2 into A1 sigma T1 to the power 4. So, and the next one is epsilon 1 epsilon 2 into 1 minus epsilon 1 into 1 minus epsilon 2 into sigma T1 to the power 4. So all these terms have got a sigma A1 sigma T1 to the power 4 as common. So if we take that as common, from the first term, what we are left with is epsilon 1 epsilon 2. For the second one, we are left with epsilon 1 epsilon 2 into 1 minus epsilon 1 into 1 minus epsilon 2. From the third one, what we are left with? Epsilon 1 epsilon 2 into 1 minus epsilon 1 square into 1 minus epsilon 2 square, plus the next term would be epsilon 1 epsilon 2 1 minus epsilon 1 cube 1 minus epsilon 2 cube. So this will be an infinite series. And if I write the sum of the infinite series, this comes out to be, this term remains the same, A1 sigma T1 to the power 4. This is epsilon 1 epsilon 2 divided by 1 minus epsilon 1 into 1 minus epsilon 2. Now if I divide the numerator and the denominator with epsilon 1 epsilon 2, what do I get? Numerator mein aa jata hai 1. Denominator, if I expand this denominator, what will I get? If I expand this denominator, this will be 1. And if I multiply this term, this would again be equal to 1. And this would be 1 plus epsilon 1. And this would be plus epsilon 2, and then I multiply epsilon 1, epsilon 2 with a negative sign now. So this would be epsilon 1, epsilon 2. Now divide this whole thing by epsilon 1, epsilon 2. So these two will get cancelled out, plus 1 minus 1. If I divide epsilon 1 by epsilon 1, epsilon 2, what do I get? I get 1 by epsilon 2, this term. And if I divide epsilon 2 by this term, what will I get? 1 plus epsilon 1. And if I divide minus epsilon 1, epsilon 2 by epsilon 1, epsilon 2, I get 1 minus 1. So this is what happens. This is the amount of energy, the total amount of energy which is sent by 1 and is absorbed by 2. That means a heat exchange that is there. A1 sigma T1 to the power 4 into divided by 1 divided by epsilon 1 plus 1 divided by epsilon 2 minus 1. So similarly, if I am talking about the amount of energy absorbed at 1 coming from 2. So what is it once again? Whatever is coming from 2, that means coming from here. Let me get my pointer. Remember what I'm talking about. Here it was whatever was absorbed on this plate. That means whatever was coming from 1, falling on 2 and getting absorbed. Now we are talking about whatever is coming from 2, falling on 1 and getting absorbed. So we are summing these terms up. If I sum up these terms and take it to an infinite value, then this one comes out to be A1 sigma T2 to the power 4 divided by 1 plus epsilon 1 plus 1 plus epsilon 2 minus 1. Now this A1, it could have also been A2 because A1 and A2 both being parallel plates are identical. So this is Q21. That was Q12 and this is Q21. Now the net rate of transfer of energy is equal to the difference between the two. That means a difference what is the difference now? This is A1 sigma, this is T2 to the power 4, and this is the term. Now if you go to the previous one, if you notice, this is A1 sigma T1 to the power 4, and this term is identical in both. So we can take that term common, and we can find out the net rate of transfer of energy from 1 to 2 is A1 sigma T1 to the power 4 minus T2 to the power 4 divided by 1 by epsilon 1 plus 1 by epsilon 2 minus 1. Now, if you think about it, that in case we have a black body, so in a black body, what will happen? Your emissivity is going to be equal to 1. So if I have a black body, just look at what happens out here. So this term becomes equal to 1 because 1 by epsilon 1 becomes 1. This term is also equal to 1, and the last one is a minus 1. So what will happen? Two of these will get 1 plus 1 minus 1 cancels out. So the only thing that we are going to be left with is this much. That is A1 sigma T1 to the power 4 into T2 to the power 4. This is exactly what we had seen. If you notice, if you go back and see this, for parallel black bodies, this is what we had seen. But since my body, in this case, what I'm considering two parallel plates, they are non-black bodies, as a result of which we have these epsilon terms which are coming inside. So it is not just A1 sigma T1 to the power 4 minus T2 to the power 4, but there's an epsilon terms become important. And since there are two different surfaces, their epsilon values may not be the same. Or it could be the same, it may be or may not be the same. Now suppose these are the two parallel plates which are non-black. But not everything will be two parallel plates. That's the simplest geometry possible. So suppose there are other geometries. Suppose we have two concentric spheres or cylinders. So two concentric spheres means, sorry, just give me a moment. Two concentric spheres would mean one sphere here, another sphere here, and two concentric cylinders would be one cylinder, and outside that is another cylinder, both having the same center. So if you have geometries like this, then what happens is that if you look at the expression now, is A1 sigma T1 to the power 4 minus T2 to the power 4, fine, into 1 by 1 minus epsilon 1 And when we are writing the next part, that is 1 minus epsilon 2 minus 1, this is multiplied by the ratio of the areas of 1 and 2. 1 could be the inner one, 2 could be the outer one, for case of spheres or cylinders, whichever one is the case. But the areas are different. But in the case of the first one, when we're talking about two parallel plates, since the areas are same, this term becomes equal to 1. So this is for two parallel plates, and this is for a case when we have two concentric cylinders or two concentric spheres or any other geometries. But the rate of heat exchange between two bodies due to radiation having different temperatures, T1 and T2, having different areas, A1 and A2, then this is how we can find out the net rate of heat transfer. Okay, before I do an example, any questions till now? Obviously, this was a long sort of derivation to reach to this expression, but this now becomes a general expression which you can use for other cases also. Anybody has a query? Fine. Then I'll move on and I'll try to do this example out here. So what is this example that we're talking about? This example that we are talking about says, this is a very practical example, you see. Liquid nitrogen, see what happens. I think most of you have seen flasks at home, that means vacuum flask, जिसमें ठंडा पानी रखते हैं या usually गर्म पानी रखते हैं फ्लास्क में घर पे छोटे बच्चे हो या senior people हो. So if you have ever seen a broken one of these vacuum flasks, and the reason they are called a vacuum flask is, and you will see that the outside of the vacuum flask is silvered. There's a silver layer which is out here, and the reason they are silvered is, we will see right now why it is silvered, because we have less emissivity out here. So we try to reduce the emissivity of that particular material, so we silver the surfaces. And the space between the two surfaces is essentially evacuated. Evacuated means there is vacuum which is maintained, and because whenever there is vacuum, the heat transfer cannot happen either by conduction or by convection. So the only heat transfer that can happen is by radiation, and we try to minimize that part as much as possible. So any kind of, because our purpose in a vacuum flask will be to either retain the heat or retain the cold, whichever one it is. We don't want heat to go inside the system, or we don't want heat to come out. So whatever the temperature is, we want it to be maintained. So in that case, we have to minimize the amount of radiation that is happening, and we remove the air between the two layers that is there. So let us see what we have out here. Liquid nitrogen boiling at 77 K. 77 K means minus 196 degrees centigrade, is stored in a 15-liter spherical container of diameter 32 centimeter. So we have a spherical container like this, and diameter of the spherical container is 32 centimeter, and we have liquid nitrogen inside this. Okay. The container is surrounded by a concentric spherical shell of diameter 36 centimeter. So now we have another shell, concentric means same center, around it. The diameter of this one, if I write it down, happens to be 36 centimeter. Then what did I say? And the space between the two spheres is evacuated. So this space, let me see if I can use another color. So this space that we are talking about, this part, this whole space which is out here, this is evacuated. Evacuated means vacuum is maintained inside the space. So if you notice that the temperature inside is 77 Kelvin, 77 Kelvin. So it is very cold, that is because minus 196 degrees centigrade, and we do not want this to get heated up, because if this gets heated up, liquid nitrogen will now turn into vapor. We do not want that, because then the pressure is going to increase. We want to maintain that the nitrogen remains liquefied. So we will try to create all kinds of possible conditions so that the heat does not enter the system. And so we put another shell around it, concentric shell as it's called, and the space between the two is turned into a vacuum. So there will be no heat transfer by conduction, there will be no heat transfer by convection. So this is how we can write this expression. So let us see what we have out here. Liquid nitrogen boiling at 77 K. 77 K means minus 196 degrees centigrade, is stored in a 15-liter spherical container of diameter 32 centimeter. So we have a spherical container like this, and diameter of the spherical container is 32 centimeter. And we have liquid nitrogen inside this. So now we have another shell, concentric shell, of diameter 36 centimeter. So now we have another shell, concentric shell, around it. The diameter of this one, if I write it down, happens to be 36 centimeter. Then what did I say? And the space between the two spheres is evacuated. Little bit of heat transfer will happen because of radiation, because that cannot be avoided. And surrounded by a spherical shell of diameter 36 centimeters, which is at a temperature of 30 degrees centigrade. So here they say that this surface is at a temperature of 303 Kelvin or 30 degrees centigrade. 303 Kelvin. The surfaces of the spheres facing each other are silvered. That means क्या बोल रहे हैं? These surfaces, this side, inside facing the inside, and this one facing the outside, these are silvered. Like you have a silver paint behind a mirror. So you put a paint out here and turn it into silver. So that has a silvered surface has got a very low emissivity, and the emissivity is equal to 0.03. So emissivity is the amount of heat that is given out by the body is based on that. So that has got a very low value, which is equal to 0.03. Now, if the latent heat of vaporization of liquid nitrogen is 201 kilojoule per kg, find the rate at which nitrogen evaporates. So some loss of energy will definitely happen due to radiation. We have to see how much of nitrogen will evaporate because of the heat that is entering the system. Also find the rate of evaporation if the surfaces were black. Instead of silver, if it was black, we can find out how much of heat will enter the system. So for this, these are obviously the first one is not a black body. So these are gray bodies, or a non-black body as we can call it. And the two spheres are not of the same size, so the areas are also different. So the expression that we are going to use is the one that we had developed in this particular case. That is A1 sigma T1 to the power 4 minus T2 to the power 4 divided by 1 by epsilon 1 plus A1 by A2, 1 minus epsilon 2 minus 1. So this is the one that we are going to use out here. So let us see what are the terms that we need in order to use this equation. Let us see that. So A1 is the area of the inner sphere, and we know the diameter of the inner sphere is 32 centimeter. Convert that into meter, it becomes 0.32 meters. And the area is pi d1 squared is 0.3217 meters squared. Area of the outer sphere is which has got a diameter of 0.36 meter, is 0.407 meters squared. So we have the areas A1 and A2 with me. Sigma value is a standard value, 5.67 into 10 to the power minus 8 watt per meter square Kelvin to the power 4. T1 is the inner sphere, which has got a temperature of 77 Kelvin. T2 has got a temperature of 303 Kelvin. Always remember, temperatures have to be put in Kelvin or the absolute scale. Epsilon 1 and epsilon 2 are the emissivities of the two surfaces. And we have been told that the emissivities of both the surfaces is equal to 0.03 each. So now if I put in all these values, that is A1 into sigma that is T1 to the power 4 minus T2 to the power 4, 1 by epsilon 1 into A1 plus A2, 1 by epsilon 2 minus 1. The amount of energy loss that we have is minus 2.5998 watts, or say about 2.6 watts. Minus 2.6 watts. So what does minus mean? That the heat that is there is coming from outside to, the heat is essentially coming from outside to inside. That is why there is a minus sign out here. Now, if I want to know what is the rate at which nitrogen evaporates, so this is the amount of energy that is coming in, that is 2.5998. This is divided rate of evaporation, that is, this is Q watts divided by lambda. What is the unit of lambda? Kilojoule per kg. So this is 201 into 1000. This is joule per kg. And what essentially means joule per second. So you have joule per second divided by joule per kg. And the answer comes out to be in terms of kg per hour, or kg, if you multiply it by that, it will be kg per second. Kg per second, and you can multiply it by 3600 to get kg per hour. So this is the amount, the value in 1 hour. The kgs of nitrogen that is going to evaporate is 0.047. So if I calculate in terms of grams, this comes out to be 47 grams evaporate in 1 hour, which is not a very large number. Ye to possible hai. Now, if the bodies were black, we use the same expression. If the bodies were black, what would happen? That epsilon 1 is equal to epsilon 2 is equal to 1. If I put this as 1, 1 minus 1 becomes equal to 0. This term vanishes off. 1 minus epsilon 1 becomes equal to 1. So what we have is this much. A1 sigma T1 to the power 4 minus T2 to the power 4. If you put in the values, this comes out to be minus 153.105 watts. That is a very, very large value. If you see the previous case, it was only 2.6. And had it been a black body, this becomes 153.105. And the rate of evaporation, again calculated, is 2.74 kgs per hour. So if these surfaces were not silvered, and we did not maintain a vacuum inside, there would be a lot of loss of energy. And the amount of energy that would be lost, the maximum amount of energy that can be lost is, and the nitrogen that can evaporate is 2.74 kgs for every hour it will evaporate. And because the sides have been silvered and it has been evacuated, this only comes down to 47 grams for every hour, which is acceptable in the cryogenic industry. Okay. Now what we do is we understand something interesting. That but cryogenic industry essentially means industries where we are essentially talking about below sub-zero temperatures. That means when we are talking about sub-zero temperatures and maintaining materials, things, equipment, everything under those particular conditions. So the purpose in these industries would be somehow to reduce the rate of heat loss. So whatever way we can do it, one would be again to silver the surfaces and reduce the emissivity, which we have seen right now. Another way of doing that is by using something what we called a radiation shield. A radiation shield. So what is a radiation shield? A radiation shield is a barrier. Let me get my pointer. A radiation shield is a barrier wall of low emissivity placed between two walls in order to reduce the exchange of radiation between them. Suppose this is one wall, which is at a temperature, wall number 1, temperature T1 having an emissivity of epsilon 1. And there's another wall, which is wall number 2, which has got an emissivity of epsilon 2 and is at a temperature of T2. If I want to reduce the heat loss between these two walls, that means we want to retain the heat, reduce the amount of heat loss, then we can put a barrier in between. And this barrier, which is shown by this orange line, has got, we are denoting it by body number 3, and temperature is T3 and emissivity is epsilon 3. So this shield acts as an additional resistance, and we can try to see how we can do this or what happens. So suppose this barrier was not there, then the rate of heat exchange between these two plates which are there is equal to A1 sigma T1 to the power 4 minus T2 to the power 4 divided by 1 plus epsilon 1 plus 1 plus epsilon 2 minus 1. These are parallel plates, so the areas are the same. Now here we say that epsilon 1 is equal to epsilon 2. That means the emissivities of the blue plates are the same, but the emissivity of the blue plate and the orange plate is not the same. That is, epsilon 1 is not equal to epsilon 3, and also similarly epsilon 2 is also not equal to epsilon 3. So if you're talking about the net heat exchange between 1 and 2, we break it up as from here to here and then from here to here. So the heat exchange between this blue plate and this orange plate, that means 1 and 3, we can write it as A1 sigma T1 to the power 4 minus T3 to the power 4 divided by 1 plus epsilon 1 plus 1 plus epsilon 3 minus 1, because the second body is the body number 3. And similarly, this steady state, so this exchange will be the same as the heat exchange between body 3 and body 2. So A1 sigma T3 to the power 4 minus T2 to the power 4 divided by 1 plus epsilon 3 plus 1 plus epsilon 2 minus 1. Now, since epsilon 1 and epsilon 2 are the same thing, same values as we had seen or specified before, these two terms, this one and this one, remains the same. It is the same thing. So they essentially will, I can say that since they are the same, they can be cancelled out. Apart from that, A1 sigma is there, and here also there is A1 sigma. So this also cancels out. So what we are left with is T1 minus T1 to the power 4 minus T3 to the power 4 is equal to T3 to the power 4 minus T2 to the power 4. So putting this together, we have that there are two T3 terms. I think the T3 terms to one side. This is bringing this T3 out here. It becomes T1 to the power 4 plus T2 to the power 4 divided by 2. So T3 to the power 4 can be written in terms of T1 to the T1 and T2. Now, if I put this expression of T3 to the power 4 in this, say, first expression out here, in this particular expression, what do I get? That Q1 is equal to A1 sigma T1 to the power 4 minus T3 to the power 4 is written as T1 plus T2, each of them raised to the power 4 divided by 2. And this is 1 plus epsilon 1 plus 1 plus epsilon 3 minus 1. Now this becomes, if I take a common denominator of 2, this becomes 2 times T1 to the power 4 minus T1 to the power 4. So 2 times becomes becomes T1 to the power 4 minus T2 to the power 4 divided by 2 plus 1 plus epsilon 1 plus 1 plus epsilon 3 minus 1. Now, if epsilon 2 is equal to epsilon 3, or we can say epsilon 1 is equal to epsilon 2 is equal to epsilon 3, that it is the same emissivities for all three of them, then this becomes epsilon 2. And if you compare this term and this term, see what happens. Here, it is A1 sigma T1 to the power 2 minus T2 to the power 4, T1 to the power 4 minus T2 to the power 4 divided by 1 plus epsilon 1 plus epsilon 1 plus epsilon 2 minus 1. And look at this term. What do I have? A1 into sigma into T1 to the power 4 minus T2 to the power 4 divided by 2 plus 1 divided by 1 plus epsilon 1 plus 1 plus epsilon 2, because I said epsilon 3 and epsilon 2 are the same, minus 1. So if I compare the two of them, I can write that Q1 is equal to Q by 2. That means if I take a similar plate as this blue plates which are on the other side, if I just place another plate in the middle, the rate of heat transfer gets reduced by half. If I put two plates out here, then the rate of heat transfer will become equal to 1/3. So this is how we can reduce the rate of heat transfer between two plates by just putting a similar plate or a similar shield in between the two of them. Even if you don't use a material of a different emissivity, I use the same one, then still my rate of heat transfer can be reduced substantially. So generally we can write that Qn is equal to Q divided by n plus 1. So number of shields I'm putting plus 1 times it gets reduced. So if I put one shield, that means the orange one, that is one shield, one plate out here, my rate of heat transfer goes down by half. If I put 2, it goes down by 1/3. If I put 3, it becomes 1/4. So this can be continued. So if the emissivity of the shield is the same as the initial plane, the heat exchange reduces by 1 by n plus 1. This kind of shield is often used in the cryogenic industry. Instead of using other fancy ways of reducing rate of heat transfer, we can do the simple calculation and a simple arrangement so that the rate of heat transfer can be reduced substantially. Now you see that when we are talking about non-black bodies, the only non-black body that we have talked about is essentially these two parallel gray plates, and we have seen that how the radiation, emitted radiation falls on from one plate to another plate. Part of it gets absorbed, part of it gets reflected, and then it falls on the next plate, and so on and so forth. It was still a simpler understanding when we are talking about two parallel plates. But when the shapes become more and more different or complicated, trying to understand the radiation heat transfer between non-black bodies become more complex. For black bodies, one thing is that we had seen that the rate of heat transfer is equal to this much. That is A1 F12 sigma T1 to the power 4 minus T2 to the power 4. The only complication in this whole thing is trying to estimate the view factor. If somehow we can find out the view factor, because emissivities for all black bodies is equal to 1, then we can calculate the rate of heat transfer between two bodies. But when it comes to non-black bodies, things become more complicated. And if the geometries are different, etc., then, and what calculations that we did, if you realize this is considering transmittance, is equal to 0. In case transmittance is not equal to 0, then again part of it will be transmitted, and we have to take that into consideration during our calculations. So when we are talking about reflections back and forth between non-parallel bodies, etc., which may not be symmetric, everything becomes a little too difficult to analyze like this. So for that matter, we now define two new terms for understanding the rate of heat transfer or heat exchange between two non-black bodies. And in order to understand this, in order to develop a general expression between rate of heat transfer, we can see that there are certain assumptions we make. So what are the assumptions that we are making? So let me get my pointer again. The assumptions that we are making, that all surfaces are considered diffuse. So if the surfaces are diffuse, means the radiation is in all possible directions. Jitne directions mein possible hai, it is there in everywhere. And they are uniform in temperature. That means each surface has got a single temperature, and the reflective and the emissive properties are constant over the surface. So any part of a surface, the reflective and the emissive properties do not change over the surface. Along the surface, it remains the same. And if it changes, then that's another story. Now, there are two new terms have now been defined. One is called irradiation and one is called radiosity. Now, let us slowly try to understand what are these two different terms. Irradiation is denoted by the letter G, and radiosity is denoted by the letter J. So what is irradiation? Irradiation is the total radiation incident upon a surface per unit time per unit area. I have shown it by this red line, that whatever radiation is incident on a surface, radiation that is falling on a surface, is known as irradiation. Jahan se kahin se bhi aa raha ho, but irradiation essentially means what is the amount of radiation that is falling on the surface per unit area per unit time. And it is denoted by the letter G. And radiosity is the total radiation leaving a surface per unit area per unit time. So total radiation that is leaving a surface, denoted by this blue arrow, is known as radiosity. Now, radiosity can include both the emission and the reflection. Now, what is reflection? I told you, whenever radiation is incident on a surface, part of it may be absorbed, part may be transmitted if it is it's a non-opaque body, and part of it will be reflected. So part of this will be the reflected one, which is leaving the body, and because and here all these cases we are considering that transmittance is equal to 0. We do not worry about transmittance out here. So an absorbance is not going to leave the body. So what is leaving the body is essentially the reflected one. And I told you that each body, because of its inherent temperature, will emit radiation. So there is the radiation which leaves the surface has two parts. One is due to the emission, due to the inherent temperature of the body, and the second one is reflection. Reflection is only possible when there's an incident radiation coming, whereas emission is possible only even when we do not have anything falling on the body, but because of the temperature of the body, there'll be some energy which is radiative heat transfer that happens, or energy that goes out, which is known as the emission. So the energy which goes out of the body comprises of two parts. One is the energy emitted and one is the energy reflected. So what is it that we see? Reflection, I told you, will depend on how much is falling on it. And what is falling on it? G is the amount of energy that is incident on the surface. Part of that is rho. That is, rho essentially would mean the reflectivity. If you remember the definitions that we had seen, that there were three things. One is absorptivity, alpha, reflectivity, rho, and tau is the transmissivity. Here we consider transmissions to be equal to 0, so tau is equal to 0. The only thing is absorption, and the other one is we are talking about is reflectivity. So reflectivity multiplied by the total incident radiation is the energy which is reflected. And when it comes to energy which is emitted, it is EB, that is the sigma T to the power 4 multiplied by the emissivity of the body. So this is the energy emitted due to the inherent temperature of the body, and this is the energy which is reflected because of the incident radiation that is falling on the body. So there is two parts. So now you know that, also you know that alpha plus rho plus tau is equal to 1. Since tau has been taken to be equal to 0, it is alpha plus rho is equal to 1. So rho is equal to 1 minus alpha. And alpha, that is absorptivity, is equal to the emissivity when we use Kirchhoff's law. So using Kirchhoff's law, we can write rho is equal to 1 minus alpha, which is also equal to 1 minus epsilon. So putting this value out here, I can write that J, or radiosity, is equal to epsilon into EB, and instead of rho, I am writing as 1 minus epsilon into G. Or if I rearrange this value, I can say that G is equal to J minus epsilon B. Epsilon into EB, I've taken it to the left-hand side. It is J minus epsilon into EB divided by 1 minus epsilon out here. This is equal to my G, or this is my irradiation that is there. So the net energy leaving, so this is the energy which is falling on the surface. This is the energy which is leaving the surface. So the difference between the two will give me the amount of energy, net energy leaving the surface. So net energy leaving the surface is the difference between the radiosity, that is J, and the irradiation, or the radiation that is falling on it, that is equal to G. So J minus G. J can be written as epsilon into EB plus 1 minus epsilon into G. Minus G is the one from here. That means this is minus. So if I rearrange this, what I will get is Q by A. Now, here I've written it as flux, that is Q by A, because it's always per unit area, per unit time, if you remember. So Q by A is equal to epsilon into EB minus G. This is, we get it from here. So if you open up the brackets, this becomes G minus epsilon G minus G. So this G and the first G will cancel out. So epsilon common le lo, so EB minus G. That means the emissivity of the, or the emissive power of the amount of energy that is under emission minus G, which is my irradiation. This is what it is. Now we can also write that if this is epsilon, EB minus G, we had found out how we can write G in terms of the radiosity. So in terms of the radiosity, where did we get this? This is where we got it. G is equal to J minus epsilon EB into 1 minus epsilon. I replace this value of G in this particular expression. So this is where I have put the value of G. And so if I take the LCM, what do I get? The numerator is epsilon B minus epsilon, sorry, EB minus epsilon into EB minus J plus epsilon to B. So these two terms will cancel out. And what we are left with is that epsilon into EB minus J divided by 1 minus epsilon. If I write it in this particular form, what I get is that EB minus J, the numerator is known as the potential difference. This is again a rate process. So this is the potential difference. And if this is the potential difference, the denominator will be called the resistance. So what kind of resistance? We are talking about surface resistance. That is, when the radiation falls on a body, whatever is going out, etc., this resistance is the surface resistance of a single body. We are not talking about a second body as of now. There's only one single body that we are talking about. And mathematically, we often write it as like an electrical network, that this is the two ends of the potential, that is EB and J. And this is the amount of the resistance between them, that is 1 minus epsilon divided by epsilon into A. So remember this term, that this is the surface resistance. This is going to be an important term that we have to look at. So this is my, so is there any other kind of resistance that we are talking about? Let's see. When we are talking about the exchange between two bodies, that is A1 and A2, two bodies, say body 1 and body 2. Okay, the first body, of course, if you notice, I have made it into the erratic shape. That means it is neither a circle nor a sphere or anything. It is just any shaped body. The first body has got an area of A1. The second body has got an area of A2. Okay, so the total energy leaving surface 1. Now we have talked about, so there will be a surface resistance of body 1. There also will be a surface resistance of body 2. What kind of surface resistance are we talking about? This is the surface resistance that we are talking about. There is another kind of resistance that when this energy passes from body 1 to body 2, there will be a resistance in the path, which we call the space resistance. So let us see what it is. How do we try to understand this? Of the total radiation that leaves surface 1, that amount that reaches surface 2 is J1, A1, F12. So this is the amount of radiation that is leaving surface 1, which is equal to my radiosity. I told you radiosity is what is leaving surface 1. This multiplied by the area multiplied by the view factor. And the total, this is from going from A to B, or the other 1 to 2. Now, if I'm talking about the total radiation that is leaving surface 2 and reaching surface 1, this is J2, A2, F21. That is, this is going from body 2 to body 1. The net exchange of energy between two surfaces, that is Q12, is equal to J1, A1, F12 minus J2, A2, F21. So this minus this, whatever is going in this direction minus whatever is coming back from this direction. And the principle of reciprocity tells us that A1 F12 is equal to A2 F21. So Q12 net can be written as taking A1 F12 common is equal to J1 minus J2. Or we can write that Q12 is equal to J1 minus J2, and you put it in the denominator, like this is my potential, and the resistance is 1 by A1 F12. This is essentially the space resistance between the radiosity potentials. So this is the space resistance between them, not the surface. Surface we have already seen. Then when it travels through the space, there's a resistance because of the space, and then it will reach surface 2, which will have its own surface resistance. So if I look at the whole exchange between body 1 and body 2, I will see that this can be understood in this way. So body 1 is EB1. From there, if you look at it, what were the two potentials? EB and J. So from the body 1, this is the surface resistance of the body, and this is J1 because we are talking about surface 1. Across the space it travels, and the potential since J1 and J2 reaches surface 2. The potentials are J2 and EB2. And the two resistances between them are 1 minus epsilon 1 divided by epsilon 1 A1. This is the surface resistance, radiation surface resistance of surface 1. This is the space resistance to radiation, and this is the surface resistance to surface 2. So if I put these resistances together and if I write the net from the beginning till the end, this becomes a case of EB1 minus EB2. And there are three resistances involved out here. This is resistance, surface resistance due to surface 1, space resistance, surface resistance due to surface 2. So this is a general expression that is written in order to understand the exchange, how heat exchange happens between two bodies. And here we are using the concept of radiosity and irradiation to get to this particular principle. There's nothing different from what we have written before, but I will get back to it. But today we are running out of time. So I will stop out here, go through all of this, all of you. And if there is any question, I will continue from this part in the next class. And when we will try to simplify this general expression and see what happens when we have specific geometries that we are talking about. So I'll stop sharing and thank you.